Le Chatelier's principle applies to a system that is already at equilibrium. So forward reaction, or rate of forward reaction, equals the rate of the reverse reaction, and the concentrations of reactants and products don't change. And Le Chatelier's principle states that if I then stress that system that's at equilibrium, the system shifts in the direction to relieve that stress. So if I apply stress to a system that's already at equilibrium, it will do what it needs to do to get back to equilibrium. And the way we say that is it's going to shift to the left or it's going to shift to the right, meaning it's going to shift towards the reactants or it's going to shift towards the products in order to relieve that stress. So the first stress that you can apply is changing concentration. If I add nitrogen dioxide to this system here, I'm going to momentarily increase the concentration of the nitrogen dioxide because I'm adding it. But that stresses the system because the nitrogen dioxide was at equilibrium. It was at a constant concentration. And so now the system has to re-equalize. It needs to go back to equilibrium. It needs to go back to where it was. And so to do that, to undo this adding of the nitrogen dioxide, the system will shift. The system will shift to the left, meaning that that nitrogen dioxide will react to produce the dinitrogen tetroxide to get rid of that extra nitrogen dioxide that I added. So the reason it shifts left is because there is more collisions between the NO2 molecules to form the N2O4. So when I'm increasing the concentration, when I increase concentration, that's going to increase the rate of that reaction, right? So when I increase the concentration of the product, that's going to increase the reaction rate of the reverse reaction. So it's going to shift left. What I mean by shift left is that the concentration of anything on the left is going to increase. So the concentration of the N2O4 is going to increase. When we say shift left, that's what that refers to. When I add N2O4, we are going to shift to relieve that stress. So we're going to use up that extra N2O4 that I added. We're going to shift to the right. Why? Because there are more collisions between the N2O4 molecules to make NO2. And so my concentration of NO2 is going to increase. If I removed NO2, so I'm going to take some of this out. It was at an equilibrium concentration. Let's say its equilibrium concentration was 1 molar. And now I've removed some. And now it's like 0.75 molar. It needs to get back to that equilibrium concentration. It needs to get back to that 1 molar. And so what's going to happen is we're going to shift to the right to make more of that NO2 to replace what I've removed. So in fact, that's kind of a nice summary of what happens when we change concentration. So the system is always going to shift away from anything you add because it needs to get rid of what you've added. The system will shift to replace anything that you remove. So looking at this equilibrium, what happens to the concentration of nitrogen monoxide if I remove bromine? So if I remove bromine, we're going to shift to replace what I've removed. So we're going to shift towards what I've removed. So we're going to shift right, which means the concentration of everything on the right is going to go up. So the concentration of the nitrogen monoxide is going to increase. If I add BRNO, we're going to shift away from what I'm adding. So it's on the left, so I'm going to shift away from that. I'm going to again shift to the right so that the concentration of the nitrogen monoxide is going to increase. In this reaction, if I add more carbon dioxide, so I'm adding more product, we're going to shift away from what I'm adding. So we're going to shift to the left. Now, if I add more calcium carbonate, notice my states here, everything else that I've done has been homogeneous, all gases. This is a heterogeneous equilibrium. And so my calcium carbonate and my calcium oxide are solid. So at equilibrium in my container, I have some solid calcium carbonate, I have some solid calcium oxide, and I have some carbon dioxide reacting. And because the concentrations of solids cannot change, they are effectively one. When I add more solid, there is no change to the equilibrium because there was already solid in there. So adding more solid doesn't make it react more. If it was going to react more, it would react with the solid that was already in there. When we change volume, this is only going to affect gases. Let me say it that way, effects. It's only going to affect gases because gases are the only thing whose volume can change. So at equilibrium, again, we have a constant concentration of reactants and products, constant amount of reactants and products, which means we also have a constant pressure because pressure of gases is directly related to amount of gas. As amount of gas goes up, pressure goes up. So at equilibrium, pressure is also constant. If I change the volume of my container, that's going to change the pressure because, as you know, pressure and volume of gases are inversely related. So if I started with a container, 1 liter container at 1 atmosphere of pressure, and that container is at equilibrium. If I double my volume to 2 liters, that's going to cut my pressure in half. It's going to be 0.5 atmospheres. The system will shift to get that pressure back up to 1 atmosphere. So the way the system responds to changes in volume and therefore pressure is by changing the amount of gas present, since gas is directly related to pressure. So this system is nitrogen plus hydrogen in equilibrium with ammonia. So I have this in a container, it's at equilibrium, and then I decrease the volume, which means the pressure is going to increase. And so the system needs to shift to get that pressure back down to what it was. And the way it does that is by decreasing the amount of gas particles present. So if I look at my balanced reaction, adding up my coefficients, on my reactant side I have 4 gas particles, and on my product side I have 2 gas particles. So when the volume goes down, which means the pressure goes up, in this case I'm going to shift to the right because that is going to bring the pressure back down. So I'm going to shift to the side with fewer gas particles because, again, fewer gas particles means lower pressure. If I increase the volume, the opposite is true. So again, we got our nitrogen plus hydrogen in equilibrium with our ammonia. And so in this case, I'm going to increase the volume, which means the pressure is going to decrease. The system needs to shift to change the pressure back, to increase the pressure, to replace the lost pressure, if you know. So we're going to shift to the side that has more gas particles. In this case, we're going to shift to the left. Now, the left doesn't always have more gas particles than the right. You're going to have to look at the coefficients. Each equation is going to be different. So considering this reaction, I have 3 gas particles on this side, and I have 2 gas particles on that side. So if I decrease the volume, that means I'm going to increase the pressure. So we need to relieve that stress. We need to relieve that increase in pressure. We need to get that pressure back down. And so I'm going to shift to the side that has less gas. So we're going to shift to the right because that has fewer gas particles, so that would decrease the pressure back to what it was. If I increase the volume, that's going to decrease the pressure. And so now I need to get that pressure back up to what it was. I need to increase the pressure overall to get it back to what it was. And so to do that, I'm going to shift to the left. I'm going to shift to the side with more gas particles. Now this one's an interesting situation because I have 2 gas particles on each side. And so I'm decreasing the volume, which means I'm increasing the pressure. But since each side has 2 gas particles, there is not a side that's going to relieve that change in pressure So there's going to be no change to the system. So kind of like my away from what's added, replace what's removed. When we're talking about volume and therefore pressure changes, if there's more space, so if the volume goes up, you're going to go to the side with more gas. If there's less space, you're going to go to the side with less gas. So considering this reaction here, which change would cause the reaction to shift to the right? Would it be changing the volume, increasing the hydrogen concentration, or decreasing the hydrogen concentration? Looking at these, here I have 2 gas particles on my reactant side and 2 gas particles on my product side. So changing the volume isn't going to shift the equilibrium either way, since both sides have the same amount of gas. I want it to shift this way. I want to shift it right. So the one that's going to do that is going to be increasing the hydrogen because it's going to shift away from what I'm adding. If I decrease the hydrogen, it would shift to the left to replace it. The last stress that you can apply to a system is changing temperature. So remember, in an endothermic reaction, heat is a reactant. Heat is absorbed, so it's on the reactant side. In an exothermic reaction, heat is a product because it's being released. So you can treat temperature changes just like adding or removing reactant or product, as long as you have heat in the right place. So if I raise the temperature, if I have an exothermic reaction and I'm raising the temperature, that's like adding to the product side, so I'm going to shift away from what I'm adding. If I have an exothermic reaction and I lower the temperature, that's like removing product, and so I'm going to shift to replace what I remove. And then, of course, the opposite is true for endothermic, where heat is a reactant. So if I raise the temperature, that's like adding reactants. So I'm going to shift away from the reactants. And if I decrease the temperature, that's like removing reactants. So I'm going to shift towards the reactants. So just treat temperature, again, like adding or removing reactant or product, depending on what side it's on. So the following reaction is endothermic. So I'm going to put heat as a reactant. So what is the effect of increasing the temperature of the reactant mixture? So if I increase the temperature, that's like adding to the reactant side. So we're going to shift away from what we're adding. We're going to shift to the right. If I decrease the temperature, that's like removing reactant. And so I'm going to shift to replace what I've removed. I'm going to shift left. This reaction is exothermic. So heat is a product. So if I increase the temperature, that's like adding to the product side. So I'm going to shift away from what I'm adding. So we're going to shift left. If I decrease the temperature, I have to replace what I'm removing. So I'm removing heat. So to replace it, I'm going to shift right. Decide whether higher or lower temperature will produce more product. So my delta H is negative 151 kilojoules. Negative delta H means I have an exothermic reaction. And so this question's phrased a little bit differently. I want to produce more product. So what it's saying is I want to shift it to the right. So would increasing or decreasing the temperature cause this reaction to shift to the right? Lowering the temperature will cause the reaction to shift to the right because it will shift to replace that heat that's being removed. This is an endothermic reaction, so heat is a reactant. Which disturbance increases the amount of product most? So increasing the temp and increasing the volume. So I have 1 gas on this side. I have 2 gas on this side. Okay. So increasing the temp and increasing the volume. Well, increasing the temp is going to definitely cause it to shift to the right, shift towards the product. Increasing the volume, however, is going to cause it to shift away from that product because there's more gas on that product side. Oh, nope. Just kidding. Pretend I didn't say that. Increasing the temperature is going to cause it to shift to the right because I'm shifting away from what I'm adding. Increasing the volume is going to decrease the pressure. There we go. So I'm going to shift to replace what I'm, to replace that pressure. So I'm going to shift to the side with more gas, which in this case happens to be the product side. So they're both shifting to the product. So probably that's my answer, but let's check the other ones. Increasing the temperature, that's going to cause us to shift to the right. Decreasing the volume, that's going to increase the pressure. So I'm going to shift away from the side with more gas. So those two are going to kind of cancel out. Decreasing the temperature, I'm going to shift to replace what I'm removing. And increasing the volume, which is decreasing the pressure, which would cause it to shift that way. So nope. And then decreasing the temperature, we're going to cause it to shift away again from the products to replace what I'm removing. Decreasing the volume is going to cause it to shift more towards the reactants. And so it was, in fact, A. Catalysts speed up reactions equally in both directions, and therefore do not affect equilibrium. So, you might get thrown a question about which way will it shift if you add a catalyst. The answer is there's no change because the catalyst shifts or speeds up the forward reaction and the reverse reaction equally. So for this exothermic reaction, meaning heat is a product, we're going to predict the equilibrium shift caused by each of the following. So if I'm adding SO2, here's SO2, I'm going to shift away from what I'm adding. So I'm going to shift to the right. If I remove SO3, I'm going to shift to replace what's being removed. So I'm again going to shift to the right. Changing volume, let's look at this. So I got 3 gas on this side. I got 2 gas on this side. So decreasing the volume, that means that I'm going to increase the pressure. I got to get to the side with less gas. So we're going to again shift right. Decreasing the temperature, that's like removing heat. So I have to replace what I've removed. So I'm again going to shift right. Catalyst is added. Again, catalyst speed up both the forward and reverse reaction equally. So there is no change when I add a catalyst.